Hi, friends. Welcome again to another episode of Beyond the Clouds Edge to Edge Transformation. Here with us today is Tony. Tony, tell us about you. How did you become the Tony Chan Carusone that we know today?
As a child, I was always good at math and science, and that just came naturally to me. Otherwise, had a pretty simple background. I didn't have any friends or family really that were strong in science or had an engineering career until my older brother got educated in engineering, and I saw all the doors that opened up for him, all the opportunities. I thought I'm good at math and science too, so that became a direction for me, a goal, a passion for me, and that's really carried through a lot of my career in a way, because starting from there, really a lot of my journey has been dictated by early success I had in academics and education. Education really opened so many doors for me, and that created a lifelong respect for education and teaching and just the importance of that. I saw the impact it could have on people, and later gave me the passion to become a academic myself and teach at the university. As I started my university education, I took mostly to topics like software, and I was studying electrical engineering, so control systems, communication systems. The thing that really tied it all together was this applied math behind it that I found it just beautiful how I could explain really practical things. I always wanted to understand how things work, and then seeing that there was this sort of elegant math that underlaid it all was really inspiring to me, really drove me forward. In hindsight, again, that emphasis on the fundamentals in my education and the maths and the sciences has been really useful for me lifelong in being able to adapt to new things and change it, everything right up to the present day where AI is changing. So I didn't really get into hardware until I got my first engineering job. And as it happened, my first summer job was wire bonding a big circuit board and putting a system together and getting it to work. And that was really formative for me. That's where I first got my hands on some hardware. It was actually a unique, fortunate opportunity I had at such a young age to play with such a sophisticated system. We were making an ultrasound imager to detect skin cancer in a hospital, and I was working on all the electronics for that. I was still passionate about systems, linear systems, and the math behind it and so on, until I had another really formative experience where a well-renowned faculty member at the University of Toronto, where I'm still a faculty member today, I was speaking to him about maybe doing research in this area, choosing this as a career. He told me to think strongly about hardware. What I realized over time was that it's in hardware and in electronic systems and IC design in particular, where a lot of the things that I found so beautiful, it's really where the rubber hits the road for those things, like communication systems. You can work your whole life on theories and ideas there, but it's really the implementers, it's the people that are putting it on integrated circuits that drive the technology and finally apply it. So that was another turning point for me and led me down this path of integrated circuit design. Eventually got my PhD at the University of Toronto and became faculty member there right out of school, teaching electrical engineering. I've had that position for over 20 years. At the same time, I was always like the combination of academic pursuits, but also working in industry. It kept me connected with real world problems, allowed me to have real world impact with my work beyond just educating young people. I was always participating in industry R&D. And fast forward to just a couple of years ago, I got the opportunity to step in as CTO at Alphawave Semi. I was very pleased to do that, and that's been the latest chapter for me.
That's an exciting journey. I remember growing up myself in farmland, and I was the first engineer in my extended family. And honestly, before I got into engineering, we all believed that it's basically how to create engines or to drive engines. So, did you go through something similar when you got into engineering school?
Well, yeah, I remember thinking that the engineer is just the person that conducts the train on the train tracks, right? Obviously, that was as a young child. There was a really positive aspect of being in an environment and a family that wasn't focused entirely on engineering. To this day, it keeps me grounded. It also forces you to think about how to explain what you're doing, which is really complicated, to lay people. And that's something I found to be super valuable for me in my career. I feel like it's one of my main value adds, really, the ability to take complex ideas and pull them together and synthesize them distill them and communicate them to people in a way that's tailored to them, meet them where they're at. Just background is a big part of that. A lot of my friends and family, that when I speak to them, they think that I'm an electrician or something and I'm involved in home wiring or something like that.
I went through similar experiences. That's one thing that inspired me to always be involved in coaching, teaching, and mentoring. Is that what inspired you to get into the academic side of things at the University of Toronto?
I really saw firsthand the huge positive impact education can have. I felt like I didn't have the benefit of connections or friends that helped me get a leg up in industry or anywhere. Whatever success I had, it was just built on the back of fundamentally doing well in school. So I really believe in the power of that, the ability to elevate people. That definitely is what led me down that path. I always saw it as a really tremendously impactful thing. Like, what could be more impactful on specific people's lives than giving them these tools and these skills to build a life on?
Most people tend to go these days from all areas of education and all areas of training towards software. And you did quite the opposite. You went from theoretical mathematics, physics, and probably even computation and system level to hardware, to IP and chip design. What inspired you to go in this direction?
In fairness, I should say it was a different time back then, as I'm not the spring chicken anymore. It was a while ago. So back then, there wasn't such a strong movement towards software engineering like we see in the past few years. But even so, I don't know if that would have really changed anything. I really recognized at some point that if I want to see these ideas in action and have an impact on the real world, that it was in the hardware that I could really do that. I always say it's ironic that young people today feel like software is more tangible to them than hardware. I kind of get it. Software is something that you can play with, and it's what you directly experience when you're interacting with technology is really the software. That's the sort of interface layer. You feel more familiar with it, more comfortable with it. And when you're engineering it, it's much quicker to have design cycles on it and debugging cycles with software, whereas hardware is abstracted from us almost intentionally. All that complexity, all that engineering is hidden from view. So it feels more like a black art to young people. But to me, it's ironic because hardware in the end is ultimately the tangible thing, whereas software is really the abstraction that we layer on top of it. The way we engineers have been so successful at masking that complexity, it's turned it into a black art. But I've always had this desire to sort of pull back the curtain and see how things really work, whether it's in technology or any aspect of life. For me, that's part of learning. And so when I did have these windows into hardware technology, and I felt like I was learning something that very few other people knew. I love that. I gravitated toward it. It also speaks to the underlying value of an education in hardware and those skills. There really are fewer people that understand technology at that level. If you're a young person thinking about a field to focus on, that implies there's fundamental value there in having that skill. It's a scarcity. Anytime you have a scarce commodity, it's guaranteed to be valuable over time.
And then you moved from academia and research into actual implementation and IP and chips and systems. What has that transition been like?
It was actually a very smooth transition for me. I've always been interacting with industry. It was an important aspect of being a faculty member. My research allowed it to have more reach and impact, made sure I was working on relevant problems, but also kept my understanding sharp of trends and R&D directions. So I was always interacting with industry, number one. Number two, I'm pretty embedded in my immediate community here through the university. After many years interacting, training so many students that go through and that ended up working in local industry. For most of that time, I was focused pretty much entirely on analog and mixed signal IP for connectivity applications, whether it's over copper cables or optical fiber. I was always researching in that area. Over the course of those 2 decades, there grew up around the University of Toronto a community of companies and really smart people working on that field in various companies, a group of founders that were people that I actually went through school with and that I count as old friends. And they founded this company in this area that I'd been researching for 20 years, and it was right in my backyard. And so many of my former colleagues and friends participating in it. It was just a perfect situation for me to step into. It's been a very smooth transition and a great joy.
Now that we're getting into very high density, there's a ton of problems. Which kinds of problems do you consider are the most important to solve? And what have we been able to successfully bring from theoretical research into practical applications?
One of the main motivators that gets me out of bed in the morning is trying to reduce the power consumption of the connectivity solutions these days. It's important to drive down the price of a chip by a few pennies. The increasing power consumption of our electronic infrastructure, that's a real motivation. And the ability to have a tremendous impact on that through my work at Alphawave is really motivating and inspiring, especially now with this arms race in building out AI, compute infrastructure, which is talked about so much in the news now, is all around us, and hundreds of billions of dollars being spent to build out everything from semiconductor capacity in order to build these chips, all the way through the supply chain and all the way out to the data centers, rolling these services out to end users. I mean, there's so much investment riding on this. It's not surprising the kind of impact that it's having on our overall energy consumption. If you think about the H100 processor from NVIDIA, which is a large GPU that's used for a lot of AI training jobs, it burns about 700 watts when it's fully operational. It's an expensive device, so it's unlikely that an operator would purchase a bunch of those chips and just leave them sitting idle for any extended period of time. You can expect that once it's commissioned, it's going to be operating most of the time at full capacity or close to full capacity. On top of that, in addition to the 700 watts burned by that chip alone, you have to factor in additional power for cooling it. So usually these are fans or air conditioning, or could even be water cooling systems. And then, of course, it's the connectivity. That's a tremendous processor capable of doing a lot of number crunching, but it's only useful if you can feed it data. And feeding data in and out of those processors consumes more power, all the networking infrastructure around it. By the time you include all that, plus the power delivery, the losses, you can double that number roughly. So it's about 1.5 kilowatts per processor that would be consumed. Next year, NVIDIA is poised to deliver about 1.5 to 2 million of these devices. And if you do the arithmetic, that means if you consider just this one model of AI processor that's being delivered by one particular company, and just the number of units delivered in 1 year, once those are all commissioned, you're talking about the power consumption of a small nation. That's really the scope of the problem. Now, you take this out 4 or 5 years down the road, we really need to look for solutions that are going to constrain this energy consumption. That's a really motivating problem. It's something that I've done research on through the university for a long time, and now the ability to work on problems at scale at Alphawave's been one of the great motivations for me there.
I worked on simulation of power devices almost 20 years ago. We had these huge cell phones that we could not even keep it in our pocket, and they would get really hot. The hot chips are really hot in those days. So, what kind of technologies are you able to bring in to make it possible to have a smaller energy footprint, to reduce the power consumption and the heat sinking and the thermal and all the complications around it? Are you able to do that in chiplets and complex systems as well?
Chiplets are a big part of the solution to this problem in a number of different ways. As we're going to scale out performance of these systems, one way that chiplets helps is it just lets us realize very large processors in a highly integrated fashion. So rather than having two reticle limited dies on two separate boards and then having to communicate between them and provide all the infrastructure around each one separately, now you can put all that processing power within a single package and then have them communicate to each other over very low power interfaces, die-to-die interfaces like UCI Express, which is a new emergent standard for connecting chiplets within a package. So chiplets allow you to save power that way and communicating information between processors. You can also take memory and incorporate that within the package as well. So now you're saving some power on the memory interface as well. and it allows you to implement different parts of that system and whatever process technology is best optimized for it. So, for example, you can have all the processing power implemented in the most advanced CMOS technology that affords the lowest possible power consumption. Meanwhile, you can have other parts of the system that don't require that to be implemented on less expensive CMOS technology. So you get this optimal combination of power, efficiency, performance, and cost. It even opens up the door to other avenues for power optimization. Once you have packaging technology that allows you to combine chiplets fabricated in different technologies onto the same package, you can start to incorporate other types of chiplets in there that allow for things like optical connectivity. Now, by integrating CMOS devices with optical transceivers, then you also can further save on power consumption rather than having these things separated by a circuit board. It's really a whole new design paradigm that we're just getting started on now as an industry. So far, that technology is only being exploited by a few large companies. Now we've hit an inflection point where the whole industry and even governments recognize that this is the next wave of technological innovation for integrated circuits, and everyone's committed to opening up the doors of innovation to the whole industry and essentially creating a more open chiplet ecosystem where everybody can innovate and participate. We're very excited about that. Alphawave's really positioned itself to take advantage of that. It's a big strategic investment we've made because we really believe that that's the way forward for the whole industry.
That's exciting. And I believe Alphawave was also one of the first to embrace RISC-V technologies. There's some reports from China that they're being used even to create supercomputers as well as AI processors. So are you able to employ RISC-V in multiple different industries?
We've actually recently forged a partnership with ARM, and we're part of ARM's Neoverse ecosystem of partners. So we really see that as a key way for scaling out compute infrastructure. We're very pleased to be enabling the use of different kinds of compute and custom silicon to create processors that are tailored for specific workloads. Yes, I do think this ability to take processor IP, mix and match it with connectivity IP that we have in order to create custom silicon solutions for different applications is going to be another huge part of the solution to the power problem I laid out. Whenever you have an application that requires so many chips that it's economically viable to develop a custom chip solution for it, it's inevitable that you're going to reap some power and cost savings compared to a general purpose solution. If you can make a custom processor for a phone, that's obviously going to be more energy efficient than just taking one off the shelf that was made for some other purpose. And so the same is true for these new workloads that are emerging around inference and training, even separately. We're psyched about this ability we have to access these IPs, combine them with our own connectivity IP, and create custom silicon solutions for some of the biggest players out there.
Bespoke silicon is becoming more common. Special purpose, it reminds you of the good old days of LSI logic, where you could make something specifically for certain applications as against general purpose processors. Is that what people are asking for lately?
Yeah, absolutely. Just to go back a little bit to the story of Alphawave, Alphawave grew quite quickly from its founding in 2017 to an IPO just 4 years later in 2021. That then fueled a further spurt of growth in the last couple of years to where we now have multiple lines of business. So one of them is we license connectivity IP to customers that wish to incorporate them into their own silicon solutions. Now we will also work with those same customers or other customers and take their unique IP and incorporate them and finish the chip together with our own IP to make a custom silicon solution and deliver it back to them. And finally, we're also developing our own connectivity products as commercial silicon to offer to the whole industry. Underlying all that is the same fundamental building blocks, the connectivity IP that underlies all that, but a big part of what we're doing now, rather than just licensing that IP out, is incorporating it into custom silicon solutions, as you said, bespoke silicon for specific applications that our customers want and need.
One of the challenges that I see is that more and more people are gravitating towards software. So that leaves a big hole in terms of the electrical engineers, computer engineers available to design these chips and systems, without which we won't really have good IoTs and AI solutions. So on one hand, there seems to be acute shortage of well-trained people. But on the other hand, there are claims that AI is going to solve everything and we don't need people, creating a lot of anxiety among potential people trying to join the industry. How can we inspire people to be there when we need them?
Anyone that's been playing with these AI tools, these large language models, and by the way, any of your listeners that haven't played with them yet, I encourage you to do so. You really want to get familiar with this technology to understand it. It's just super fun. If you have been playing with it, you'll see that one of the things it's really amazing at is helping develop software. So if anything, that seems an area where AI can really be leveraged to assist people in developing software more quickly, more efficiently. Companies can leverage it to be more efficient in their software development operations. I certainly see that. On the hardware side, we're seeing a lot less of that. The main challenge there is that, unlike software, where you've got something like GitHub and giant open source repositories of tons of software that we can train models on, they can quickly become better than the best coder in the world just because they've looked at every piece of open source software that's ever been written. The same's not really true for hardware designs. There's very little that's open source, especially in advanced nodes, especially on the cutting edge. I can't even say that there's any one company that has enough of a library of such IP to effectively train their own model to do a lot of the tasks that are needed for a high performance IC design. I'd never say never, and I'll never say such things are impossible. Technology is always evolving in fast and new and surprising ways, of course, but it certainly seems to me, and all the early indications are, if you're actually playing with the technology, you'll see that it's more resistant to that. So I do see, again, that persistent value and being able to understand hardware and design it going forward. So when I'm in front of a classroom or just talking to friends with children, I'm always preaching the value of the hardware skill set in electrical engineering.
So, Tony, you worked on all kinds of interesting things from software systems and hardware systems, even control systems. Was there any particular project or any particular field you found the most interesting or the most challenging?
What I'm doing now is probably the most interesting stuff that I've ever had a chance to work on. We're really working on the very cutting edge of optical and electrical, very high speed connectivity solutions. So these are essentially like modems. If you think back, I'm old enough to remember the first modems that came into our homes that were operating at a couple hundred kilobits per second. There was a lot of signal processing going on to enable that under the hood. The thought that now we're doing that at hundreds of gigabits per second, it's just amazing. And moreover, we're doing all that in such a tiny silicon footprint that we can integrate hundreds of these all onto a chip and enable tens of terabits per second of data coming in and out of these AI processors. It's really thrilling when you are able to understand it at all the levels of hierarchy involved, everything from the amazing device physics that's been done to enable emerging CMOS technologies like gate-all-around technologies, and what's coming past that, like backside power delivery, and then move on up to analog circuit innovations, for example, that have been ongoing for decades and yet still happening today. At the architectural level, you've got new DSP systems and algorithms and power reduction techniques, and then you've got firmware and control systems running on top of that, optical technologies and devices, packaging technologies, the full stack here, and being able to be at the intersection of all that and have all that enable something like these AI models that have captured all our imagination is really cool. That's what's motivating me today.
It's exciting, Tony, talking to you. You're doing some really amazing things at Alphawave. All power to all of you, or maybe low power to all of you. We need to conserve power. Thank you for giving us a quick introduction to the challenges and the opportunities that are in the foreseeable future. We will need good engineers. AI cannot solve it, at least until we create the next level of systems. There is no shortage of work to do. So thanks again. And to people out there, this is why I talk to people from different vantage points. People have done different things because it's such a complex world we live in. There is no shortage of work. I don't see us sitting and twiddling our thumbs, at least in the next 50 to 100 years. Even to create these systems is a lot of art. If you have unique perspectives, if you are seeing challenges that cannot be solved, if you're interested in talking about what's bugging your community or the solutions that you have adopted, would love to hear about it. Thanks a lot, Tony, and I look forward to meeting you again.
Thanks very much. Thanks for the great conversation.